volume, so the volume of gas that's adsorbed at some standard condition, at different standard conditions corresponding to a monolayer. And then you have you have a reference pressure. So you basically have a reference volume and a reference pressure, and from that you can calculate a response. If you do a point measurement, what we're after here typically is the surface area. So what you would do is you would try to measure this volume Vm, okay? You would try to measure this volume Vm. Once you have that, and using Na as Avogadro's number, you can calculate the surface area. So Vm comes from the previous page. It can be extracted from the adsorption isotherms. I won't go through the theory, but it's a pretty straightforward method. But again, you could even see within the method, it's a relative method. It's a comparative method, right? It's not necessarily giving you the actual true surface area. Another technique that I'll briefly cover is FTIR. Stands for Fourier Transform Infrared. FTIR is a method that really collects an infrared spectrum and does some analysis to it. And what you're trying to do is to identify species that have particular infrared signatures, and you can do some quantification of the amount of those materials that are in the sample. Right? So FTIR devices are used a lot in studying polymers. They're off-the-shelf components that you buy, but they're typically done to look at the type of material that you have. In some cases, looking at the degree of polymerization of materials as well. The last technique that I'll cover, because I'm almost out of time, is Raman Spectroscopy. I think you probably all know where that was invented, right? And there's wonderful stories about C.V. Raman. I don't know if you know this, but when he actually did his first Raman measurement, he communicated his result to Nature by telegraph. In that telegraph, he wrote, "This is going to win the Nobel Prize," right? And then when it did win the Nobel Prize, they wrote to him and said, "You've won the Nobel Prize, and now the event is coming up very soon, so please do your booking for the ship to take you to Sweden as soon as possible," right? And he wrote back and said, "I already have my ticket." Right? Anyway, so Raman spectroscopy, or Raman scattering, is an extremely useful approach, especially for solid-state materials, although I use it for solid-state materials, and I think that the interest here for energy materials is in the solid state. But it's also useful for gas phase studies and even biological materials. The methods are the applicability is vast. Essentially what happens here is you shine a light on a surface at a certain frequency, at an excitation frequency, and there's a slight adjustment to or can be a slight adjustment to the light that comes back, that scatters back, okay? And that slight adjustment has to do with the interaction between the light and vibrations, atomic vibrations in the material that come from these bonds that we talked about. And that slight shift, right, it's called the Raman shift, can give you information about the bonding in a material. So why is that important? Why would I want to know? Well, again, we like to know about not just the elemental composition of what we made, but how the atoms are arranged. And so Raman is a very, very useful technique to tell us that. So it's the energy diagram is shown here. You have IR absorption, which we talked about a moment ago. Rayleigh scattering, it has no effect. It's an elastic process. There's Stokes and anti-Stokes scattering that are classified within Raman. And essentially what happens is the delta, the change in energy, you see that there's these two energy states with the Raman. That change in delta comes from the interaction with a vibration in the molecules or in the solid state material. In our case, in the case of my group's work, we're interested mainly in the solid state. So here again, I tried to use the same paper as much as possible. This is again that paper on graphene, just to show you that all of these techniques, this is most of what I'm showing today came from one paper. We had to go through the laboratory and do all these methods in order to put it into the paper. Here's the Raman, the Raman shift. This is of the graphitic material, and what you see is you have a G peak. That's what we look for if we want to have graphene or graphitic type material. We look for a strong G peak. That happens at about 1600 inverse centimeters. There's also a D peak, which is typically bad. We want a low D peak. D can stand for defects. In some cases, it's also the diamond peak is embedded in there as well. And then there's a 2D peak as well, which is a resonant peak of the D peak. And the connection between 2D and G is something that a lot of folks have looked at to tell you about the quality of the graphene that you have, or in some cases the number of layers that you have. There's some way to correlate these things. Ajay Sood down at IISc has done some really good work on that. And I mentioned at the beginning of the lecture about the spatial resolution. So Raman is something now you can put inside of a microscope, and you can do fairly small spot sizes. Here I think we've got, this is in microns. The figures on the right are actual Raman images or Raman maps of a surface with a resolution of just a few microns, which is quite good because Raman uses visible light typically, right? So you're not going to be able to get below the diffraction limit. So using visible light, you're going to usually see a resolution of around 1 micron. In this case, it's a little bit, it's about that. It's about 1 micron. But here we're looking at A and B. Here the A curve is the D peak, the B curve is the G peak, and then we have the 2D, and then we have the ratio of 2D to G. And you can see from this map, I mean, why would you map it out? Well, you'd want to know how uniform your material was. Right? That's what it can tell you as well. You can see in this case it's not bad. We probably have something on the kind of on the left side here that's a little bit different. Who knows what that is, right? You could go in deeper and analyze that part of the material if you so desired. So just to close things off, this is showing that chart again about material characterization. I only covered a small fraction of that first graph, right? But these are, I think what I covered was the most common techniques and certainly the most accessible techniques. And even then, it's not cheap to do really anything that we talked about here, right? It's a big expensive machine that you have. I think what I would like to conclude with though is just having a machine that allows you to push a button and get data, a lot of data, is not enough, right? Good sample preparation. Ensuring that you have sample-to-sample consistency. We call that repeatability. Doing the test a few times over to make sure that you think that you have what you think you have, right? Those are the kinds of things that make a good practitioner out of the world of science. The machine is just that. It's just a tool. It's how you use it that counts. And with that, I will be happy to take questions. Thank you very much.
Sir,
yeah.
In XRD, you said about doping. Again, I call that as doping. The one you said about boron and nitrogen.
It's like doping, yeah.
So, we see that the peak has decreased. The intensity of the peak has decreased, or there is a shift in the 2 theta degrees.
Yeah.
So like, can we say that there's a sort of a lattice enlargement in that?
Could be. Yeah. Yeah. You could see. You can correlate the 2 theta signal to lattice strain. That's one thing that you can look for with XRD. So doping, if you have interstitial doping in particular, then you will start to see these kinds of strains, but you won't see them consistently because the dopants are distributed, right? And so you'd see some variation. And so doping would tend to smear out the strength of a peak and widen it. And that's something you could look for. Yeah. Question here? Yeah.
I have a couple of questions. The first one is that we talked about the surface structure, and then we said that we are measuring the force on that cantilever based on the atomic distances. So when we prepare the sample, is there a possibility of having ridges, the components that what the mechanical engineers call which give rise to friction, for example?
Yeah. So it's important when you have ridges in atomic force microscopy. One of the things, or some kind of surface roughness, the tip is important. The geometry of the tip becomes important as well. So you're not going to be able to resolve surface roughness that is finer than the kind of the sharpness of your tip. And so you can actually, if your tip is larger than the scale of your roughness, you won't even see the roughness. It will look smooth. And that's, but normally when we roughen surface, the way that, I'm a mechanical engineer too, I roughen a surface with sandpaper first, right? And so that's usually much larger scale roughness than what you'd have in a atomic force microscope tip. Yeah.
The second question would be, we talked about various measurement techniques. So, for example, fluorescence techniques and diffraction techniques, and then we also have something related to infrared. So how do we differentiate what we are measuring? Is it based on energy?
Yeah. So, in general, the question has to do with the spectral range. And so I think that to be a good material analyst, you have to be comfortable with shifting from between spectral quantities. So energy, you saw some of the things that we were looking at that were in energy space. Some of the things that we looked at are in wavelength space, and yet others are in frequency space, right? And it becomes confusing at first for people who are having to shift, but it's really a function of the custom, right? The custom that different groups had when they developed these techniques from the early days. But really, they're essentially the same things. Whether I talk about a wavelength, a frequency, or an energy scale, you're talking about a spectrum of a carrier, of usually a photonic or electronic carrier.
Going along that same question,
One more.
when we talk about infrared, we are essentially measuring the bond strength somehow.
Yeah. Well, it's a little bit more complicated in that the bond strength, okay, is manifested in the frequency, okay, the frequency of vibration, but it also has to do, so that frequency of vibration is what you can excite with infrared, and that also has to do with the mass of the atom. So it's not just the bond strength. You have to know the bond strength is usually the frequency is a square root function of the bond strength and the mass of the atoms. So it's the bond strength divided by mass, square root. Yeah.
So it's a very basic question. So I'm working with microgrill fuel cell. So we have electrode and which is made up of some graphene or maybe some carbon cloud. So there is a bacterial biofilm around the electrode. So I want to see, I want to check the morphology for that. People have used in literature like for SAM. They have seen what kind of bacteria, maybe rod shape, maybe circle. So which type of technique I can use to characterize, what is the interaction biofilm is doing with electrode and how I can see the morphology?
Yeah. So the question has to do with a heterogeneous, a very complex, it's not a simple question, it's a complicated question, it's a complex structure. And so, you can't really, most of the techniques we talked about would be difficult. The two techniques that I would look at are AFM, and there's some nice work on atomic force microscopy with biological materials, and then scanning electron microscopy. I think those are the two main ones. I think if you tried to do, for example, a BET analysis, you have to be able to take your sample into cryogenics, and that would change the biological structure, I'm sure. Yeah. Yes?
In the XPS data, you have shown that there are some peaks there. And is there any relation that the 1s peak intensity, the counts per second intensity, should be higher than the 2s or 2b? Or
Yeah, the deeper you go, the harder it is for the electron to come out. So usually you're having your valence states that are the most active, but it's a fairly complicated. It's in general a complicated process of exciting an electron out of a material. There's a work function involved as well. So I don't know if there's any good rule of thumb for that.
in the data itself, in the carbon 1s peak was higher than the
Right.
So
Yeah.
that contradicts.
Yeah. Well, it depends. So if you have, I mean, the 1s state is going to always be occupied, so at least it's always there. That may be some reason for the change.
Professor?
Yeah.
Nowadays, SNOM and AFM